All right, today we're going to talk about two different ideas here. The first idea is related to the if-then statements we've been working with this week. And so we're going to talk about different laws of logic that have to be true with these if-then statements. And then we're going to talk about some different properties that we're going to use going forward in geometry. So those are the two things we're going to talk about. We're going to start with talking about these if-then statements. And we're going to have two different laws, detachment and syllogism. Detachment is our first one. The law of detachment says that if the hypothesis of a true conditional statement is true, then the conclusion is also true. And this is kind of the idea, the conceit behind these if-then statements. And so this is basically talking about giving an example. Talking less about the broad example of here's what's generally true about, for example, complementary angles, and honing in on a specific example of here, take a look at these specific complementary angles. And that means we can make the conclusion. So it tells us that if I look at a specific example, if the hypothesis applies, then the conclusion is also going to apply. If the hypothesis doesn't apply, then the conclusion isn't going to apply. So this will make more sense when we look at an example. All right. So we have the general statement, the general if-then statement. If an angle is between 90 and 180 degrees, then the angle is obtuse. That's true because that's what an obtuse angle is an angle between 90 and 180 degrees. Okay, so that's our if-then statement. We're talking about a general. Here's how we know if an angle is obtuse. Now we're going to zoom in specifically to say the measure of angle R is 155 degrees. So now instead of talking about generally angles between 90 and 180, I'm talking about some specific angle R here that we know is 155 degrees. And so what conclusion can we make? Well, we can make the conclusion that angle R is obtuse. How do we know that? Because the angle is between 90 and 180. Next example says, if you get a speeding ticket, then your parents will take away your car. So here's your hypothesis, and here's your conclusion, comes after the then. And now we're looking at a specific example of you. You got a speeding ticket on your way to school. So what does that mean is going to happen? According to the statement, you got a speeding ticket. You know what that means. Parents are taking away the car. So it's honing in on a specific case, specific example where the if-then statement applies. That's all that detachment means. It's just, here's a specific example. Next is the law of syllogism. Law of syllogism takes two different if-then statements that are related to each other and combines them together. And the way that we can combine those together is if we have two statements that are linked by some hypothesis or conclusion. Basically, what you're looking for is that the conclusion of the first statement is the hypothesis of the second statement. That's what creates this link in the chain that'll link the two statements together. It looks like if P then Q and if Q then R tells me if P then R. I can cut out the middleman and just say, just start with my first hypothesis and end with my last conclusion. So the final product of the law of syllogism is going to be one if-then statement. We're taking two if-then statements and combining them into one. So here's our two if-then statements. If Cubs win the wild card, then they advance to the division series. If they advance to the division series, then that means that they will play the Milwaukee Brewers. And so this statement in blue being the same, again, the conclusion of the first being the hypothesis of the second, lets me link those statements together and turn them into one sentence. If the Cubs win the wild card game, then they're going to play the Brewers. And this is just creating and mashing these up together to create one statement with the first hypothesis and the last conclusion. So these are ideas and laws of logic that we usually use already without even thinking about it. If an example applies in a statement, and I told you an angle is 155 degrees, for example, and asked what kind of angle it was, you would be able to say obtuse without me having to say it's the law of detachment. So what I'm more worried about is that you can apply and identify which one is the law of detachment and which one is the law of syllogism. Less so than you being able to write out these statements. So take a look at these two, and this is the skill I want you to make sure you have. And to see, here are two statements. One of them is detachment, one of them is syllogism. See if you can pick out which one is which. Well, the first one here takes two different if-then statements and combines them into one. And so this would be the law of syllogism. And the second example is applying a specific case of x being 14 to the if-then statement. So is x greater than 12? Well, yes, it is. And so that means x plus 9 has to be greater than 20, which 14 plus 9 is 23, which is bigger than 20. So it's taking a specific example and applying it. So that's the law of detachment. So this first one is the law of syllogism, taking two if-then statements, combining them into one. And the second one is the law of detachment, applying a specific example. Next page. Next, we're going to look at some different properties that are going to be useful to us in geometry. And this first idea is a very, very simple one, but a very important one. It says that any real number, segment, angle, measurement is going to be equal to itself. It's the same as itself. This is called the reflexive property. This one's going to be really important. And so this reflexive property says that A equals A. And so if I have 5 over here and I have 5 over here, then they're the same. That's all this is saying. Very simple idea. If I have a segment A to B, then it's equal to itself, its own segment A to B. And you might think, well, why are we going to use this? Well, because there are times where we're talking about the exact same segment or the exact same angle or the exact same thing in a diagram in two different ways. And so in the next chapter, when we talk about triangles, there's a lot of times where we're going to be talking about a common side or angle that's shared in the two triangles. So for example, in this red and blue triangle, they both involve this green angle. So we can talk about this green angle in the context of the red triangle and this green angle in the context of the blue triangle. And so this reflexive property is going to allow me to say, hey, well, those are the same angle, so it's got to be the same. And same thing in this other diagram. This time, I could talk about, I have two triangles, this triangle here on the left and this triangle here on the right. And so I could talk about that side in the middle on the left triangle and the side, that same side in the middle on the right triangle. And I can just say, well, that's the exact same side. It doesn't matter which triangle I'm talking about, it's the same side, and so it's going to be equal to itself. Measurement is going to stay the same. So that's all we're saying when we look at the reflexive property, but it's going to come up a lot. So something equal to itself, A equals A to B equals A to B, 5 equals 5, that's the reflexive property. The next one is the symmetric property. And the symmetric property says that if we have some statement of equality or congruence, then we can take the order and we can switch them. And it still holds true. So for example, here's a way that you already use this, is that if I give you the equation 5 equals x plus 3, what a lot of you do, well, we're going to subtract 3 from both sides, but what a lot of you do when you get down to the answer is that sometimes we don't like this 2 written first. We usually like x equals, and so we just write it as x equals 2 without even thinking about it. This step is the symmetric property. The symmetric property is what lets me do this, what lets me switch that order, and it's still true. And again, these may seem like obvious things, but let's take something like an inequality. In an inequality, if I had 2 is less than x, and I wanted to switch this order, x and 2, I could not say that x is less than 2. I can't just switch the order like that. I also have to flip the inequality symbol. So the symmetric property doesn't work for inequalities. So it may seem like an obvious thing that, of course, we can switch the order. That works with the equal sign, but there's some operations in math it doesn't work for. So that's why we bother saying that it's true with equals. Now, something that is going to be true in these inequalities is what's called the transitive property. So the transitive property is actually really similar to the law of syllogism that we talked about earlier. If A equals B, that basically if 2 things are set equal to the same thing, then we can say that they're equal to each other. So when we did it as if-then statements, it was if P then Q, and if Q then R means if P then R. That was syllogism. And so the transitive property is going to be very similar. It says that we can take 2 different things that I know are the same and make them equal to each other. And so if I have, the common link is the important part here. So I have these 2 different segments that I know are both equal to C to D, A to B and E to F. I don't know about their relation to each other, but I know that they compare the same way to C to D. That means that they have to be equal to each other. There's no other choice. Once C to D is 5, A to B and E to F are also both 5, so they have to be equal to each other. For angles, if angle A equals angle B, and angle B equals angle C, then angle A equals angle C. But the more basic way to write it is if A equals B and B equals C, then A equals C. So let's look at some examples here. Name the property of equality this statement illustrates. Again, this is much more vocabulary than anything else. If measure of angle 6 equals measure of angle 7, then the measure of angle 7 equals measure of angle 6. So these statements got switched around. So what lets me switch these around? Well, that's the symmetric property. Next, if J to K equals K to L and K to L is 12, then that means J to K has to be 12. So this is taking 2 different bits of equality and making them equal to each other. That's the transitive property. And W equals W. Well, that's saying that W is equal to itself. That's the reflexive property. The reflexive property is actually going to end up being the most important one here. Having something equal to itself. That's the one we're going to use the most often. I want to end these notes by talking about some different definitions and theorems and properties that we have talked about so far in these first two chapters. And I put a star by what I think are the most important ones. So for definitions, we have definition of a midpoint. Midpoint is going to split a segment into two equal pieces. Segment and angle bisector, again, split into two equal pieces. Definition of complementary and supplementary angles. You should know what those are. Complementary adds to 90, supplementary adds to 180. We have segment and angle addition postulate. Looking down, again, the ones with the stars are the most important ones. So we have pieces adding up to the whole. That's the addition postulates. But then we have the linear pair postulate and the vertical angles theorem. And we're going to look at a lot of different diagrams that have vertical angles and linear pairs. And we're going to need to know that, hey, these are vertical angles, so they have to be congruent. These are linear pairs, so they have to be supplementary. And then the properties that we talked about here, the reflexive property is going to be the most important one. So that's it for these notes. Make sure you get them turned in to me, and I'll talk to you more soon.